Hi everyone, welcome to a new topic here in ChemE 122, and for this week we are going to be tackling the volumetric properties of real fluids. So this now would involve the actual calculations of the real volume of fluids. Okay, so recall from our previous discussions that we have calculated the volume or the molar volume of gases using the ideal gas law or using steam tables for liquids, for water rather. Okay, now this time we'll now answer ano ba talaga ang real relationship between volume, pressure, and temperature, okay, for gases, and paano nga ba nakukuha yung mga steam table values or even other thermodynamic property values na nakikita natin in many different tables. Okay, so to start our discussion on the volumetric properties of real fluids, recall our definition of equations of state. And equations of state, these are equations from the name itself that relates the pressure, okay, of the fluid, okay, with the molar or specific volume of the fluid and the temperature of the fluid, okay, for any pure homogeneous fluid, okay, of known composition in equilibrium states. Okay, and you now have three variables: pressure, volume, and temperature. Okay, and based on a degree of freedom analysis for a complete fluid of known composition, you can relate one of these properties in terms of the other two independent properties. Okay, so typically, pwede mo si V as a function of P and T, pwedeng P as a function of V and T, or pwedeng T as a function of P and V. And the simplest equation of state that we have available is our ideal gas law. And again, our ideal gas law, PV is equal to RT, okay, where V is the molar volume, okay, and R is our ideal gas constant. And our assumptions for the ideal gas law is this applicable as the pressure approaches zero or very low pressures. Okay. We also assume that there are no molecular interactions between the molecules of our gas, and the volume of the molecules are negligible compared to the total volume of our gas. And we have the following values of our gas constant, which is tabulated in SVA and other multiple references. Okay. So with the ideal gas law, we have actually maximized our discussions for this. Okay, recall your ideal gas process calculations. However, some of those calculations we have done, okay, are not exactly representative of real life values. Kasi these ideal gas law is only applicable for low pressures. So what if high pressure na? So let's say starting from 5 bar and above, medyo nagiging inaccurate na yung solution natin for the molar volume of of gases. Okay, so we now need to have multiple other equations to describe the relationship of the pressure, volume, and temperature. Now, one of the simplest empirical equations that we have is called our virial equation of state. And the virial equation of state, this is somewhat similar to your heat capacity relationship. Okay, para A plus BT plus CT squared and so on. Okay, it's a polynomial relationship between PV, okay, and maybe pressure and the volume. Okay, so the PV is equal to the following expression. So A plus BP plus CP squared and so on. So pwede mo tong gawin plus DP cube plus EP4 and so on. Okay, or you can also express this such that B is equal to AB prime and C is equal to AC prime. So PV is equal to A, quantity 1 plus B prime P plus C prime P squared and so on. Now, A, B prime, and C prime, these are all functions of temperature and the type of substance. So for each substance, iba yung A, iba din C, B prime, C prime, and so on. So these constants are temperature and substance dependent. Okay, so very generic or very general itong virial equation of state natin. You can actually simplify the virial EOS for ideal gases. Okay, for ideal gases, B prime and C prime are all equal to 0. Okay, so diba, PV is equal to A times 1 plus B prime P plus C prime C squared and so on. Okay, if B prime and C prime and so on are equal to 0, this whole term will just be A times 1, okay, where A is now equal to RT. Okay, kaya very generic itong Virial EOS. So A can be just repressed as RT. So R is a function of the substance. But in this case, R is the universal gas constant. So applicable siya for all different types of gases. Okay? And T is the temperature. Okay? So now for our discussion on the real gas volume, we define a new quantity called the compressibility factor. I denote the compressibility factor to be Z, and Z is defined as PV over RT. Okay, so therefore, for ideal gases, Z is approximately equal to 1. So Z will give us the relative deviation between the real volume of the gas, okay, and the ideal gas volume. So instead of comparing the molar volumes, we could compare the compressibility factors. Okay? And in other terms, you can express the compressibility factor as the ratio of the real gas volume divided by the ideal gas volume. Okay, and using the Virial EOS again, so diba, Z is equal to PV over RT, but PV is equal to A times this whole expression. Okay, but now we have derived that A is equal to RT. Okay, so if A is equal to RT, therefore PV over RT, lipat natin sa kabila, is equal to 1 plus B prime P plus C prime P squared, and so on. Okay, and this is equal to Z. So you can now express the virial equation of state as a function of the compressibility factor. Imbis na PV, pwede siyang Z is equal to 1 plus B prime P plus C prime P squared, and so on. Okay, so this is one form of the virial EOS, which is in terms of the pressure. Okay, so function of pressure. Pero again, Z is a function of this PV over RT again. Okay, so polynomial function of pressure itong version of Virial EOS. But there's also another version of the Virial EOS, which is a polynomial function of the volume now. Okay, so in this case, 1 plus B over V plus C over V squared. So the values of B prime or B and C prime or C and so on will depend on what equation that you will need and the tabulated values for each substance. Okay, and there's a relationship between B prime and B, which is B over RT, and C prime is the following. Okay, so we don't need to worry about the conversions or actually the values. Okay, you don't need to memorize any values for the virial coefficients. Okay, another info for the virial EOS is that the term B is usually referred to as the second virial coefficient, and C and C prime are usually referred to as the third virial coefficient. Okay, and the first virial coefficient is not used kasi 1 lang naman siya. So using the Virial EOS, pag meron kang either B prime or C prime, you can use this first version. Or kung meron kang B and C, you can use this version. Okay. And there are multiple forms of the Virial EOS. So, diba, this is an infinite summation. So there are terms, we can truncate this to the two terms. So kapag two terms lang, tinuncate, this is called the two-term Virial EOS. So the two-term virial EOS is only up until the second virial coefficient. Pero meron tayong three-term virial EOS which is until the third coefficient. Very rarely na umaabot doon sa fourth virial coefficient. So usually two-term or three-term virial EOS lang yung ginagamit for most calculations. Okay, so now some note on the virial EOS. So if you now have this plot of Z as a function of P, okay, mapapansin tayo at low pressures. So at low pressures, if you take the slope of the line, okay, for different temperatures, okay, mapapansin natin na medyo linear at the start yung relationship between Z and P. Okay? So if you take the derivative of the virial coefficient holding T constant, okay, for you can now have the first derivative, and as you can see, as P approaches 0, or if the first derivative at P is equal to 0 is just equal to B prime. So constant ang ating slope, okay, at low pressures, and C prime and D prime is equal to 0. So with this, typically, you can now have the virial EOS truncated to two terms, okay, which is semi-valid actually at low the subcritical temperatures up to saturation pressures. So at low pressures, valid na pwede mo gamitin na Z is equal to 1 plus B prime P lang. Okay? Or pwede mo siya express as Z is equal to 1 plus BP over RT, where B is yung in terms of volume na Virial EOS. Now for the three-term Virial EOS, okay, typically, ito yung range of applicability niya. Okay, so typically ginagamit sa three-term Virial EOS below the critical pressure of a fluid. Okay, and again, C is the third virial coefficient, and it's a function of the type of the substance and the current temperature. So if you know the temperature and you know the substance, read from the table kung ano yung virial coefficients niya. And you also have other forms, the virial EOS. So this is known as the Benedict-Webb-Rubin equation of state. Okay, so you can read more of these extended virial equations on multiple references. Okay, so let's have one example on how to calculate the real volume of a gas using the virial EOS. So we have the reported values, the virial coefficient for isopropanol vapor at 200 degrees Celsius, okay, given CB and CC. Okay, and now calculate for the molar volume and the compressibility factor for isopropanol vapor at 200 degrees Celsius and 10 bar. So first, using the ideal gas law. Second, using the virial EOS truncated to 2 terms, so hanggang B lang. And then using the virial EOS truncated to 3 terms, so ito hanggang C na. Okay. So first, we have our ideal gas equation. So V ideal again is equal to RT over P using the ideal gas law. And just substituting the values here. So R is 83.14 cm cube bar per mole. Okay. Temperature is 473.15 Kelvin and the pressure is 10 bar. So from here we can get the ideal gas volume, which is 3933.77 cm cube per mole. Okay. And syempre, ideal gas, so Z is equal to 1. Okay. So next up, we have the two-term virial EOS. Okay, so for the two-term virial EOS, we have Z is equal to PV over RT, which is equal to 1 plus B over V. Okay, so let's substitute some values. So be careful with this. Your units have to be consistent. So ginagawa ko lagi. So dapat yung mga volume naka-cm cube dito. Okay, yung pressure dapat naka-bar. Ayan, tapos syempre temperature naka-Kelvin. And syempre naka-gram mole tayo. Okay. So with this, ito na yung ating two-term virial EOS. Okay. And then what we can do now is multiply both sides by V. Okay, to rearrange this. Okay, so you have this expression and then ilipat lahat sa kabila, you now have a quadratic equation. Okay, so you will now obtain two roots. So kukunin mo syempre yung positive root. Okay, so solving the quadratic equation and getting the correct root, you can get V is equal to 3497.35 cm cube per mole. Okay, and to get Z, okay, Z is equal to V over V ideal. So 3497.35 divided by 3933.77, which gives us the actual compressibility factor of 0.8890. Okay. And last, for the three-term virial EOS, okay, so ito yung equation natin for the three-term virial EOS. And again, multiply both sides by V squared. Okay, and rearrange para magkaroon tayo ngayon is a cubic equation of state. Okay, so we have a cubic equation and solving for the roots and obtaining the correct root, okay, which should be one closer to the ideal gas volume. So kung ayaw nyo mag-solve ng cubic EOS, cubic equation, or mag-solve ng quadratic equation, kung gusto nyo mag-shift solve, okay, since gas dapat to, your initial guess in yung pag mag-shift solve kayo should be the ideal gas volume. Okay. Yan. So, hindi lang basta-basta nag-i-input ng initial guess mo nag-shift solve kasi baka ibang root yung makuha nyo. Okay? So, you now have the cubic equation. Okay? And solving for the correct root, you can now have V is equal to 3487.74 cm cube per mole. And again, obtaining the compressibility factor, can now get Z is equal to 0.8866. Okay? So, medyo comparable yung results natin for the 2-term virial and the 3-term virial EOS. Kasi at 10 bar, hindi pa naman siya ganoon kataas na pressure. Okay? Right, so that's it for this first part of our lecture. And the next part will now involve more equations of state, okay, which are applicable to a wider range of uh, gases. Kasi dito, sa ating equation of state ngayon sa Virial EOS, you need to have the actual values of B and C for different substances and for different temperatures. Okay, so medyo hassle yun. So maghanap ka ng table of B and table of C for all other components. So we now need to have a slightly more general approach to our calculations. So ito yung one of the limitations ng ating Virial EOS. Okay, so that's it. Thank you for listening to this first part of our lecture.